In this video, we'll look at how Gauss's law applies to conductors. Gauss's law provides important theorems about conductors. First, it tells us that all the excess charge on an isolated conductor is going to lie entirely on the outside surface of that conductor. Even if the conductor has a cavity or a hole within it, there's no charge is going to exist on the inside surface unless there's another charge encircled by that cavity. And we can show that with Gauss's law. So let's discuss this isolated conductor. We're saying about an isolated conductor, it must be in static equilibrium. That means no charge is in motion. Electric current is defined as charge in motion, and electric current is a form of energy. That's our electric energy. So if we had an electric field inside an isolated conductor, remember our conductor has free electrons. So those free electrons would be forced to move by the electric field, and that will give us a perpetual current or perpetual form of energy, which does not exist. So we know that to be the case. So what happens when an isolated conductor is charged? If we imagine placing a charge on this conductor, let's say we place a positive charge on this conductor at this point, what we know is that that charge is going to move. The free electrons in the conductor will be attracted to this charge. So we'll have a free electron that will come maybe from up here. It'll be attracted, it'll move down here, and you'll be left with a hole, which is essentially a positive charge, a lack of electron. So that would happen here. It would happen maybe from over here, left with a hole, and over here we're left with a hole, and we end up with a positive charge around on the surface. So an electric field does have to appear initially for these charges to move. For these, if we have this positive charge here and these negative charges then move to it from these different locations, an electric field sets up initially to move these charges. So that excess charge, we're saying, is going to redistribute itself until the net electric field internally is equal to 0. So that net electric field, that's the vector sum of the electric field due to the charges inside, due to these free electrons, and outside, any outside electric field that's present is going to create a net electric field internally here to be 0. Well, once these charges move, what stops them from moving? When we know that electric field, that force, is going to have an acceleration. So why does it suddenly stop moving? That's due to drag. That's due to resistance in the conductor, which dissipates the kinetic energy. That resistance is similar to friction in mechanical friction. So superconductors are a material that scientists are working on. When we get things very cold, their conductive properties increase, so their resistive properties decrease, and ideally if you have 0 resistance, then once you get a charge in motion, it can continue to move. All right, so how does we show this with Gauss's law? Hopefully that all makes sense to you, but we can prove it with Gauss's law. If we know empirically, again, that the electric field internal to this isolated conductor is 0, then what we want to show is that there's no charge internal to this conductor. So what we can do is set up a Gaussian surface. So if our outside copper surface is here in red, and we set up this Gaussian surface just inside the inside surface, and we can use Gauss's law to look at what is the enclosed charge. So we're trying to find the enclosed charge. This flux, this closed integral of E dot dA, that's the flux through this Gaussian surface represented here in black. So we want to look at the electric field in the surface. Remember, our area vector always points outward, right, and is perpendicular to our Gaussian surface. So we have a lot of these little dA area vectors going in all different directions, since this is not a symmetric shape. But we want to know what is that dot product with the electric field. Well, the electric field is 0. So if the electric field is 0, then the flux must be 0. so the charge enclosed must be 0. Epsilon naught can't be 0. What's epsilon naught? Epsilon naught, that's our permittivity constant in a vacuum, 8.85 times 10 to the negative 12. It's, farad per meter, but in terms of units. So if there's no excess charge inside here, and that's where we place the charge, where is the charge? We can move our Gaussian surface. If we continue to push it outward, let's push it so it's literally right on the surface of the conductor here. Well, the electric field is still equal to 0. If it's equal to 0 inside, there can't be any flux through. So the electric field is still equal to 0, so the charge is equal to 0. So if we take that Gaussian surface and we move it just outside the surface of the conductor, well, now we could have some flux. We can't say that the electric field is 0. We can still, now we have to do our E dot dA product, and all these, again, little different dAs around our closed surface, which we have just shown a two-dimensional surface. In fact, we're looking at this planarly, but we have a three-dimensional surface, which we need to imagine. But now, in order to determine the flux, the electric field that's parallel with each of these area products, the sum of them all around the volume flux, or excuse me, the surface area flux of the three-dimensional surface, that's going to be equal to the charge enclosed divided by epsilon naught. So this is not going to be equal to 0 because the charge enclosed is not going to be equal to 0, but we've shown that all that charge has moved to the outside surface. So let's look at if we have a cavity in our conductor, can any of that charge lie on the inside surface of this cavity? So again, we can use our Gaussian surface. We can take our Gaussian surface and we can put it just inside the inside surface of the cavity. If we go to apply our Gauss's law, that flux, our closed integral of E dot dA, the electric field here has got to be equal to 0. If that electric field is 0, then our dot dA is also going to be equal to 0, which means our charge enclosed must be equal to 0. And even if we take this Gaussian surface and we continue to move it, and let's say we move it just, even on the inside cavity or just inside, we're still going to be here we're enclosing no charge. If it's right on the inside surface, the electric field is still 0. So all that charge enclosed must reside on the outside surface of the charged conductor. All the excess charge on the outside surface. What if we take none on the inside surface? What if we take this cavity and we continue to make the cavity larger so we have less and less conductor? We continue to apply that Gaussian surface. There's still 0 electric field inside the conductor. So we can continue to remove the conductor, and what we can be left with is only the charges. The electric field wouldn't change at all. It would remain 0 inside this thin shell of charge, and it would remain unchanged at all the external points. So what that tells us is the electric field is set up by the charges, not the conductor. The conductor is just providing this initial pathway for the charges to take their initial position. This concept here, this very thin shell of charge, could even be a mesh of charge, a mesh of conductor, or a mesh of some type of copper material, let's say, is a type of conductor. This is the concept of a Faraday cage, which is a thin metal shell, and is typically just made of a mesh instead of a solid conductive material, and it prevents stray electric fields from getting inside. It can prevent strong electric fields from creating signals inside the cage, so that's why it's used as metal casing around our computers or electronic devices. It's also the principle that makes it reasonably safe to be in a car. Most cars are made of metal. I suppose more are made of plastic these days, but it makes it reasonably safe to be in a car during a lightning storm. If you've been to the Museum of Science, went to the electricity exhibit, they have a huge Van de Graaff machine that collects huge amounts of charge on its ball surface here. It's brought up through mechanical methods. We bring charge up to this ball. It throws down a long, thin lightning type rod and throws lightning at a man in a cage. And this man doesn't seem to be touching the cage, but the man at the Museum of Science literally touches the inside of the mesh, and he doesn't get shocked because this is performing a Faraday cage, not allowing this electric field to go internally. That's a very important concept that we've proven here with Gauss. What happens if we have an isolated uncharged conductor in an existing uniform electric field? So this shows a spherical conductor inside an electric field. It looks like it was perhaps a uniform electric field, but what happens to the conductor is the conductor attracts the electric field lines such that each of these lines are going to land perpendicularly on the conductor, and we're going to end up with a polarized conductive object. In this case, since it's a sphere, we'll have the same amount of negative charge on one side as positive side on the other. And it affects the electric field, but there's no electric field internally. It does affect the electric field externally. Internally, this electric field is equal to the source electric field. This might be a big plane of positive charge over here, and maybe it lands on a big plane of negative charge. Whoops, we'll do the same amount of charge over here. That's our E naught. What happens internally is this electric field, remember we have superposition of electric fields, so this is an electric field here that's pointing in this direction. This is our E prime between this positive charge and this negative charge. So this net electric field is in fact our E naught due to the external electric field, and our E prime due to the electric field set up internally by the polarization inside the conductor. If it's not a spherical object, we will still get this polarization. However, remember, all these electric field lines have to land perpendicularly onto an object like this, so this conductive object. So where we have a tighter radius, we're going to have more electric field lines. So more electric field lines, that means our electric field will be of higher magnitude here than it will be over here. But still internally, we're going to have our electric field is equal to 0. We'll still have an E prime, and we'll still have an E naught, and our E will equal E naught plus E prime will equal 0. And of course, we need our vectors because we're summing vectors. These electric fields are pointing in opposite directions, and so that the superposition lends us to have 0 electric field. So that's another very interesting property of a conductor in an existing electric field. That's it for this video. In the next video, we'll look at the electric field just outside a conductor, and we'll solve some problems using Gauss's law and conductors.